All right, let's get into it. We are going to pull back the manhole cover on something we all depend on, but, probably never think about: the humble sewer pipe. And it turns out designing even a simple sewer line is this really fascinating puzzle. We're finding the cheapest route. Well, it's about a lot more than just digging the shortest trench. I mean, seriously, how hard can it be? You just connect a few dots, make sure gravity does its thing, and you were good to go, right? Well, as we're about to see, the world of civil engineering is way more complex, and honestly, a lot more interesting than you might think. So, this isn't some made-up problem from a textbook. No, this is the Goodwin Avenue sewer line. It's a real-world benchmark that engineers actually use to test out different design ideas. The goal seems simple: connect these 4 manholes with 3 pipes for the absolute lowest cost possible. But there's a catch. You've got to follow the rules. And that leads us straight to the engineering equation. This is the big balancing act, right? You're trying to keep the cost of building the thing as low as possible, but you're up against a whole bunch of real-world physical constraints. Every single decision you make, how deep to dig the trench, how wide to make the pipe, it pulls that final price tag in one direction or another. So what goes into that total cost? Well, it pretty much boils down to 3 big things. First, excavation. The deeper you have to dig, the more money it's going to cost you. Simple as that. Second, the pipes themselves. Bigger pipes, longer pipes, you guessed it, more expensive. And third, the manholes. Just like the digging, the deeper they need to go, the more they're going to add to the final bill. The real trick is trying to minimize all 3 of these at the same time. Okay, so here are the rules of the game you have to play by. The pipes, they have to be buried deep enough so they're safe. The water, it's got to flow fast enough to carry everything along with it, but not so fast that it starts to wear down the pipes themselves. The slope of the pipe has to be just right for gravity to do its job. And, of course, the pipes have to be big enough to handle the busiest times. But here's the real kicker. For each section of pipe, there are multiple possible paths. The number of combinations gets astronomical, fast. And that's when you need something a bit more powerful than a calculator. You need a really smart algorithm. So, to crack this puzzle, researchers decided to pit 2 different mathematical strategies against each other. Let's meet our 2 optimizers. These are 2 algorithms with totally different ways of searching for that one single lowest cost solution. So on one side, we've got the GRG algorithm. You can think of this one as a local hill climber. It's really fast and really efficient. It basically finds the closest hill, a pretty good solution, and it just climbs right to the top. But the problem is, it might completely miss a much higher, much better peak that's just a little further away. Then on the other side, you've got PGSL, which we'll call the Global Explorer. This one takes a different approach. It uses randomness to send scouts all over the entire landscape to find the absolute highest peak, the true best solution, even if it takes a little bit longer to find it. So the stage is set. We've got our problem, the Goodwin Avenue sewer line, and we've got our players, the speedy hill climber and the thorough global explorer. It is time for the algorithm showdown to see which one can design the cheapest system that still follows all the rules. And boom, right away, we can see they came up with different answers. What you're looking at here are the 2 final designs. In blue, that's the path that the GRG algorithm, our hill climber, came up with. And in red, that's the path from the PGSL algorithm, the Global Explorer. Now, they both get the job done. They connect all 4 manholes, but they do it in slightly different ways, choosing different depths and slopes for the pipes. So the big question is, which one is cheaper? Well, the numbers really don't lie. The GRG algorithm's design clocked in at $16,830. But the PGSL algorithm, it found a way to do it for just $15,688. That is a clear win for our Global Explorer. And let's be really clear about what that means. Just by picking the better algorithm, the engineers saved $1,142.75. On a relatively small project, that's a cost reduction of almost 7%, just by using a smarter way to search for the answer. It really proves that how you look for a solution is just as important as a solution you end up with. Oh, this slide is perfect, because it shows us why PGSL won. See that blue line? That's our hill climber. It finds a good solution pretty fast, but then it gets stuck there. It's called a local optimum. It's the best option in the immediate area, but it's not the best overall. But look at the orange line, our Global Explorer. It keeps on searching, it keeps exploring, and eventually it finds that much deeper valley, the true lowest cost, the global optimum. It's the perfect picture of the difference between good enough and truly the best. So look, saving $1,000 on one little sewer line is cool. But what's the bigger picture?
Why should we care so much about the math behind all this invisible infrastructure?
Well, as the researchers themselves put it, this isn't just some fun math problem. This stuff gives real, valuable insights to engineers and city planners. The whole point is to build our cities in a smarter, more efficient, and more sustainable way. And that all starts with making better, data-driven decisions on every single project, no matter how big or small it seems.
And that right there is the real takeaway. I mean, just imagine scaling this idea up. That 7% saving on this one little project, what happens when you apply that thinking to all the new pipes and roads being built in a growing city? It could translate to millions, maybe even tens of millions of dollars saved. And that's money that can go back into things we all use, like parks, libraries, and schools.
It really makes you wonder, doesn't it? If we can find these kinds of savings and efficiencies in something as basic as a sewer line, what other invisible systems that keep our cities running, like water networks or traffic light timing, could be totally transformed with just a little bit of smarter math?